Hello everyone and welcome to part 3 of this week's lecture. In this part we are going to look at different flow measurement devices that are based on Bernoulli's principle. More specifically in this part we will talk about pitted tube, and in part 4 we will look at orifice meter and venturi meter. Okay. As I said, we are only going to look at flow measurement devices that are based on Bernoulli's equation. We are not going to talk about all the possible methods that we can use for flow measurement. And when we are saying that flow measurement devices that are based on Bernoulli's principle, so the idea is that when a fluid is, for example, moving in a pipe or in a system, and if the fluid is going to accelerate or decelerate, it means that it's going to change in velocity, and that change in velocity is going to cause a change in pressure. And we can measure that change in pressure by using, for example, the devices that we discussed in lecture 2. And then we can use that change in pressure through Bernoulli's equation and convert it into the form of fluid velocity in the system. Okay. So Bernoulli's equation consists of three energy terms, but what we are interested in this part of the lecture is only between conversion between pressure energy and kinetic energy. Okay. So this is the more general form of Bernoulli's equation, that is the energy per unit weight, but we can also write it in this form, that is energy per unit volume, as we saw in part 2. And each of these terms in this equation, because this is a dimensionally homogeneous equation, so each of these terms should have a unit of pressure. Okay, so the P is what we call static pressure, and that is the pressure that you feel, for example, when you're flowing with the fluid. And then you have the dynamic pressure due to the velocity of the fluid, and if we deaccelerate the fluid and bring it to a stagnation point, and that pressure that you feel at that point is the dynamic pressure. And then we have the last pressure, that is the hydrostatic pressure, due to the weight of the column above a certain point, and that's what we discussed in lecture 2, for example. So we have different terms of pressure. And before we go into detail of pitted tube, I want to introduce the concept of stagnation point and stagnation pressure. And here on the right hand side, you can see that you have a system here, and here you have a solid object. And around that solid object, you have fluid is flowing, and it is simulated by using this dye. And these streamlines, for example, are different layers of the fluid. Okay. And at point 1, you have velocity u1, p1, and at point 2, you have velocity u2, p2. And if you see here, with that is represented, the velocity represented by this vector, for example, here, and that shows that when you are at point 1, the velocity is high, but as you go towards point 2, the velocity decrease, and at point 2, the velocity becomes 0. Okay, and the reason for this decrease in velocity is not the viscous effect, is because the fluid comes to a stand here, okay, at this point, and then some of the fluid move here and some of the move downward. But at point 2, that is the nose of this this object, the velocity is 0. Okay, so this point is what we call stagnation point, where the velocity becomes 0. And as it says here in this sentence, that the center of the streamline impinges on the leading edge, and the flow, for example, decelerate to 0 velocity at point 2. Okay, so this is flow, not flow, sorry. So if you now try to apply Bernoulli's equation between point 1 and point 2, and if you make assumptions, for example, that there are no loss or no loss term, and then both of these points have same elevation, so you can simplify this Bernoulli's equation in this form. And then you have the dynamic pressure term and the static pressure at point 1, and the same on point 2, for example. And as we know that at point 2, the velocity is 0 because the fluid is stagnant, or fluid is stops here. So we can write u2 as 0. And then we have final equation of P2 is equal to sum of dynamic pressure plus static pressure from point 1. Okay. It means that as you are moving from point 1 to point 2, the dynamic pressure that was half rho u1 square actually converted into static pressure at point 2. Okay, so the pressure at point 2 is larger than the pressure at point 1 because that dynamic pressure converted from point 2 to static pressure at point 2. Okay, and that's what it says here. And this pressure at point 2 is what we call stagnation pressure, and P2 is larger than P1 by this factor half rho u1 square. Okay, so that is the concept of stagnation point and stagnation pressure. And so that you can relate it better, for example, if you take out your hand, for example, out of the window when the car is driving, you feel a force on your hand. Okay, and that force in part is kind of comes from the stagnation concept or stagnation pressure. It means that the high velocity air that is moving comes to a standstill at your hand or the palm of your hand, and that is the conversion of dynamic pressure to the static pressure that you feel on your hand. Okay, and in aerodynamics, for example, we call this pressure drag, and it is different from viscous drag that is due to the velocity effects. So we can use the concept of stagnation pressure in a device that is called pitot tube or pitot static tube. And actually, it is a device that uses the difference between stagnation pressure and static pressure to measure local fluid speed. Okay, so how it looks like? So it looks something like this, and this is very commonly used on, for example, on planes and air jetliners to measure the velocity of the air, for example. So here you have, for example, an inner tube, and that is connected to one leg of the manometer, and then you have an external tube that is connected to the second leg of manometer. And at the inner tube, at the entrance of inner tube, the velocity that is, for example, the air or fluid that is coming from point 1 to point 2, its velocity becomes 0 due to the stagnation effect, as I explained in the previous slide. And then you have point 3 that actually is just measure the atmospheric pressure or the pressure, the static pressure that is in from the environment. Okay, if you take the difference of these two pressures, the stagnation pressure and the static pressure due to the surroundings, the change in height reflects the change in pressure, and then by using the Bernoulli's equation we can convert this change in height or change in pressure to velocity. Okay, so let's have a look at it, how we can do that. So at point 2, the fluid with the density rho is brought to a standstill, as I said, and this is called a stagnation point. And assuming the height difference between point 2 and point 3 is negligible because they are at the same height, so we can simplify Bernoulli's equation. That is the stagnation pressure, and then we have pressure at point 3 and point 1 that are essentially the static pressures due to the surrounding, and they are exactly the same. And if you say, for example, that u3, the velocity at point 3, you take it as u, that is a more general term. So we can write that from Bernoulli's equation, we can prove that P2 is equal to rho u square over 2 plus P3, as we saw in for the slide of stagnation pressure. And we can write this equation in the form of pressure difference, that is P2 minus P3 is equal to the dynamic pressure. Okay, so exactly the same as we saw in stagnation pressure slide. Now we can also perform a pressure balance on this device, for example, across X and Y, like we did, for example, in lecture 2 for manometers. So we know that the pressure at point X should be equal to the pressure that is, for example, because this tube, this leg is connected with the inner tube. So the pressure that is P2, that the pressure at point 2, plus the pressure due to the height h. Okay, so this is the height h, for example, from here to here. So you have pressure at X equal to P2 plus rho g h plus delta h. Okay, And similarly, we can write for point Y that the pressure at point Y here is equal to pressure due to point 3, that is the static pressure, plus the hydrostatic pressure due to this height above this point Y, that is rho GH, plus rho of the black fluid, that is rho fluid G delta H. Okay, just like we did in the case of manometers. So exactly the same. So if we know from the isotropy of pressure that these two pressures should be equal, so we can compare them, that the pressure at point X should be equal to pressure at point Y because that they are the same planar height. We can write it in the form of differential pressure, that is P2 minus P3 is equal to the difference of densities times gravity times delta H, that is the height difference between the two fluids. But we already know that P2 is also equal to rho u square over 2 plus P3 from the stagnation analysis, and we can write this equation as here. And now we have two equations with same P2 minus P3, so we can equate these two equations. We have this equation here, and if you rearrange this equation in the form of u, you get the velocity of the fluid at point 3, that is 2 rho f minus rho times g delta h over rho of the for example air. Okay, in this case, for example, if we are using it for air. Yeah, so if that is the velocity here, so this is how we can actually use the measurement of pressure to calculate or measure the velocity of the fluid inside this pitot tube. And as you can see from the equation that this is a point value. There is no, for example, radius of the pipe or anything. So if you are measuring the velocity of the fluid in a pipe, you will get a point value. Okay, it means that if you want to get an average of the fluid velocity, you need to move this pitot tube at different heights inside this pipe here, and then you can measure velocity at different points and then take an average of that velocity in the end to get the average velocity of the fluid. Okay, and you will also do a lab experiment, for example, for pitot tube. And so this is the pitot tube what we discussed, but it can also be simplified in this form, for example, here. So here you have again the same concept. You have a pipe here, and this is a tube that is equivalent to this stagnation point 2. So the fluid that is flowing here will comes to a hold, and that is the stagnation pressure. And if you connect another piezometric tube here, that will give you the static pressure. Okay, so these two are exactly the same, just in two different configurations. And as you can see here, that when the fluid is flowing, you have higher pressure on this leg, that is the stagnation pressure, compared to the pressure on this side, and that is why the fluid is moving from right to left. Okay, and in the lab you have this kind of representation of pitot tube. Here you have, for example, this device in a pipe, and this pipe, for example, here you have this is your static tube. Okay, so that is, for example, representation of this leg, and then you have this leg, that is the stagnation pressure measurement. Okay, so by, for example, moving this tube inside this pipe at different heights, you can actually calculate velocity at different points inside this pipe, and then you can take the average of all the velocities as you measure, and then calculate the average velocity of the fluid inside the pipe. And in next part we will look at orifice meter and venturi meter.